today, because they saved the best to last. It's parallel session number 9 of the Moon missions, chaired by myself, Pamela Clark, and Douglas Curry. And I will begin, give the first talk, and introduce Russell Cox, and then Douglas Curry will take over in terms of chairing the session. Okay, my talk is already lined up. Very good. So what I'd like to talk about, which I alluded to yesterday at the focus group meeting, for those of you who were there, the LunarCube concept. Do I actually have to be focused, talking right into the mics for you to hear me? Okay. Let me see if I can move around a little bit. All right, I can do this. Yeah. Let's just try to remember to stay close to the mics. I'll hear myself, so it should be okay. There are a number of people. This is a collaborative effort. A number of people involved in it, some of whom are named up here. The take-home message basically is the problem: how to meet ambitious exploration goals and provide cutting-edge science while expending fewer resources. I'm not interested in fewer resources and having an impact on exploration and science. We want it all, basically. And the proposed solution is LunarCube, which is an extension of the very successful and affordable Cubesat model, and using that concept with critical technologies developed to support deep space access, to facilitate access to the Moon as an entree to all other targets in the solar system. And I turn, what? Okay, good. Why the Moon? Well, I don't really have to explain that too much to this group, but basically because it's very close, relatively accessible to compare to any other target, represents essentially the environment and surface of the Moon are analogs for most of the real estate in the solar system in virtually every way. And the lunar surface is thus an ideal test bed, because it is an analog, for key technologies we will need to go virtually anywhere, and also because it's an analog for so much of the surface, and we know the surface is very interesting now based on the last 10 years of data from the Moon, that high plasma, very cold temperature surfaces have processes we don't yet fully understand that have implication for solar system origin. Therefore, we can provide high quality science by going to the Moon. All of these things are good reasons. So I would say any sound approach to planetary exploration, especially if you want a lower cost in a constant cost or decreasing cost environment, would involve access to the Moon, particularly if you can do it in a sustainable way. And that's actually the idea behind the Cubesat model. This is just an illustration of why it is that we have all these micro niches, especially as you approach the lunar poles, that represent a lot of the real estate in the solar system. Over here is the ranges of temperature for the Moon. Over here you see, I'm trying to get this the pointer to work here, that there are a number of bodies that have conditions within this range, and therefore surface chemistries with a variety of different compositional variations in the sources of material on these different bodies. And of course, again, I don't really repeat to this group, but we basically have a, this is a better pointer? Oh, okay. Thank you. Yeah, that is much better. Okay, so we have a variety of missions that have provided measurements over the last 10 years that indicate the presence of surface water, surface in various forms actually, and to depth, and volatiles, in some cases identified, in some cases not identified, and supporting evidence of the role of volatiles by the finds on Mercury of confirming polarized deposits and the presence of sulfur. And the Moon, of course, as everybody in this room knows, again, has a lot of small heritage. So we've flown a number of missions already that have been mentioned in the course of this meeting. There are a lot of proposed small framework missions to the Moon. I don't have to mention all of them here. Some of these have more development than others, but there are not. This is a small smattering of missions that people have actually thought about in terms of going to the Moon. Okay. For those who aren't aware of it, I'd like to talk a little bit about what Cubesat actually implies as it now exists. So the idea behind Cubesat is a standardized bus, and it's a Class D mission. Class D meaning relatively low cost and high risk. Now, how do you deal with missions like that if you have low cost and high risk? The way you do it is by having a standardized bus with standardized interfaces that basically by flying it many, many times, you figure out what works and you use it in future standardized buses. And that approach has been so successful that the cost of a completely standard CubeSat with the freight cost for launch, which a lot of educational institutions can get, is about $50K. Now, we're talking about more capability. I'd say we could estimate that with greater capability, and I think I'm being conservative here, if you want to increase that by an order of magnitude and talk about something approaching $1 million for a single CubeSat, think of the difference between the cost of that and what we now pay for most missions. So, if we're talking hundreds of millions, which is typically what NASA will fly, in some cases, tens of millions in the small sat category, that's actually, and we, with the core technologies we'll develop, we will increase the capability. I'm thinking about CubeSats that have more capability to cost about 10 times as much to allow deep space access. So I'll talk about what those core technologies are in just a moment. Form factors, well, the U in this case is a 10-centimeter cube, and the design is not only standardized but modular, so you can basically increase by use. The largest system now for packaging and deployment that's used in standardized CubeSats is called PPOD. It's provided by Cal Poly and San Luis Obispo, and their largest system that they can support is 3U, which could be 3U or 3-1U CubeSats. And Wallops has developed a design all the way to phase B for a 6U system, and JPL is working on somewhat larger framework CubeSats. So there's options out there. We're at the beginning now, but it looks like, using the standardized model, we have lots of ground room here for seeing what's going to work. What we do need is feedback from payload and instrument developers to find out what the minimum requirements are and what the limits are in terms of how small we can get. That's going to be important to get. Technology impact is usually low. However, that being said, the standardized bus is what keeps the technology impact low. You can fly a high-risk experimental payload that is actually potentially a high technology risk, but the bus is standardized. Okay. How do these need to be enhanced? How do these capabilities need to be enhanced for deep space? Here's several ways, pretty encompassing, but there could be some additional areas. Increase the duration, probably, that can usually be measured in months to years. Form factor to grow to at least 6U. Active attitude control, which implies propulsion. That's because you can't take advantage. You can't do passive attitude control, which is done in Earth orbit now, basically by taking advantage of the Earth's magnetic and gravity fields. It have to be active propulsion, active attitude control, which will require a propulsion system. This could be made sustainable in the sense of lowering bandwidth by onboard intelligence to do routine multi-platform operation, which is one of the things that we have proposed to test with the Edison program in Earth orbit. Information transfer is a key area here. You must have more robust communication, CNDH, to support onboard processing, which again, to be made sustainable, implies some onboard intelligence to do your processing and selecting of information to be sent down to lower your bandwidth requirement. And a big one for operating on the lunar surface and in a lot of other places where it's very cold and dark for extended periods of time is thermal mechanical design. Greater hardness to space radiation. There are a variety of potential solutions that are already employed in deep space operations today, both hardware and software. And ruggedness for extreme thermal variations. A beginning point, which we've explored, is using mil-spec components for electronics, which can operate at much lower temperatures and survive at much lower temperatures. But ultimately, this will involve using state-of-the-art cold temperature electronics, which actually do exist at this point, but haven't been used systematically to populate whole systems, and developments in power for deep cryo operation. Now, I'm assuming that because of the expense and time frame for radiothermal generators, where the price alone is going to price that out of most people's price tag and mitigate all the advantages you get from Cubesat. So frankly, I think we need some other options, and there are some technologies at low TRL that are on the table that could potentially be used. So we thought about this actually to the extent that we see it as a multi-phase process, and again, at every stage of the way here, you may notice that it isn't just about technology, and it's not about science, it's about a partnership. That's always the case with Cubesat, and it'll be the case with LunarCube. So we're talking about starting off with stage 1, which basically means getting from Earth orbit to cislunar space. One example of where this could be an effective application would be in communication stations using multiple platform nodes at different locations to facilitate communication outside of Earth orbit. And that would mean, in terms of what I just talked about, the 5 different areas, that would basically mean having some development, some degree of development in all these areas, testing the technologies as you go along. Getting to the lunar surface, we call stage 1.5, basically with at least some capability, means you have to work a little bit on number 5, which is better survival with cold temperature operation. And there are options for how you get to the lunar surface. You can think of a multi-platform or single CubeSats, as well as a nano-rack kind of approach, which is being proposed by Astrobotic, for at least a limited duty cycle on the lunar surface. The final stage involves being able to do full operation 24/7 on the lunar surface. It means pushing forward all of these key technologies, fully implementing onboard intelligence, and being able to do deep cryo design with power systems that would support it. This, again, some of these capabilities could be tested en route to stage number 2. You're not putting everything down here. You develop these things systematically as you go along. So ultimately, full operation would be possible. And the vision, basically, and this is something that, that DARPA has in mind, and people that think about Cubesat have in mind, is essentially a platform, a multifunctional workstation, if you will, instead of a one-of-a-kind spacecraft, that's like a smartphone with interchangeable apps. And that's basically where we're going with the technology. That is the direction. It's almost a juggernaut. That's where, and when you get to that point, what happens is, since you lower the economic barriers, you create a sustainable market, which would help us enormously. We would no longer be, squabbling over the decreasing dollars that exist every year to support planetary science. You could actually have a sustainable market, which is one of the reasons why so many people want to play in the private sector, because already in Earth orbit, we're virtually at a sustainable market when it comes to Cubesat. Because there's so many people can participate that there's a market to build components to support it. I just want to mention in a few sentences the importance of onboard intelligence. We actually are proposing something to test it, which we're calling SmartSat, through the Edison program for the Office of the Chief Technologist. And it's based on these technologies. We have a Goddard patented synthetic neural system, which has already been partially implemented for NASA ST-8 and DARPA F6, Moorhead State University bus, and 60 gigahertz RF system, which is multifunctional. Omni antennas for distance and direction, interspacecraft communication, and atmospheric sounding. That's nice. I like that multifunctionality. And then Honeywell has developed very small, powerful, low-power, dependable multiprocessors, again, tested in NASA ST-8 and DoD SMD TechSat. And finally, propulsion system that, in fact, has also been tested through DoD Air Force NanoSat program, and which has sufficient delta V and ISP to support our proximity operations. JPL is working on something that's supposed to support deep space operations that's supposed to be available in 2014 in the way of a microthrust propulsion system. You don't have to read this, but this is just another way of looking at some of these core technologies that we develop in my comments on when and where these will be developed. I'm sure this will be online, so a place for people to look at it, but we're kind of in this framework here. I put the earlier framework because a lot of development has already gone into many of these technology areas. There's a very capable CubeSat bus, deployment systems that already exist. There's a systematic way to get things as secondary payloads into orbit. There's already been developed in things like propulsion systems, advances in guidance, navigation, and control. And we see over the next 10 years that if given enough sufficient support and technology development, these things could be pushed forward, and we could easily be in phase 2 in 10 years in all of these areas. We now have microthrust propulsion systems that can be tested and operate effectively to do proximity operations in Earth orbit, or we will have them within the next couple of years. And this is a very key technology. And we've provided that we have continuing to support in some form for onboard intelligence. We can end up easily over here with phase 2 capability of operating 24/7 on the lunar surface. Technologies tested that can considerably reduce the cost barriers for all deep space exploration. One of the things that I mentioned earlier was that We need to look at potential instrument payload status that could be supported by Cubesat. Actually, the Cubesat people, the people who want to go into deep space with the Cubesat model, want people who do instrument development and payload development that give feedback on what some of the hard limits might be over here in terms of what we could anticipate in the way of mass, volume, power, and bandwidth reduction, given core technologies that can support that are being developed by, for example, the Office of the Chief Technologist. And I've just made a few notes here, but I'd be happy to get anybody's feedback who have expertise in any of these areas to look at where they expect to go, or concepts they may have in some areas where there are particular issues with mass, power, or volume, such as in gamma ray or neutron spectrometers, for example, or mass spectrometers. I happen to know that there's actually a MEMS concept at about TRL3 for a mass spectrometer that was proposed for a lunar instrument, for example. And you can't always find concepts published in the open literature. So there's a lot of information here that people have already thought about to solve these problems. And finally, please don't read this, it's an eye chart, but what I wanted to show here was that it actually looked at some of the costs for Cubesat. Right now, I mentioned some of these costs earlier for what now exists for standard Cubesats. Basically, what we're talking about, which is a very sophisticated CubeSat with more core technologies now under development, not standardized yet. So we're really talking about the millions of dollar range here. Millions of dollars, basically, maybe somewhere between 8 and 9 million for 3 3U CubeSats. Okay, keep that in context with cost for what is projected for development according to the decadal survey over the next 10 years. And this is basically what I have here. So we're talking about down here, one-of-a-kind Class A missions, proposed 5 Discovery class, 2 Frontier class, 1 flagship class. Problem is that all the candidates are above the cost cap for the flagship mission. We're talking about 2-point-something billion each for each of these. So we're talking about, this is just for the missions part of the planetary budget, over $6 billion here, close to 7. Now compare that to cost for, even if we're increasing these by a factor of 10. We're still talking about tens of millions as opposed to these costs. And if we're talking about onboard intelligence and we have swarm ability for autonomic support during flight, which means that ground control does not have to be involved in telling a spacecraft how to get from point A to point B, the bandwidth savings that will involve, and the capability is, for 3-dimensional spatial and temporally resolved studies or interferometry with a lot of control. And that's basically where this technology could go, which means much more high-powered science. So you're basically getting everything we want. And probably developing, if we continue to support core technologies in about 5 or 10 years, many of the basics already in place to do this because there's pressure from the Earth orbiting CubeSat community to do it also. Questions? Do we have time for questions? Maybe not really. We can take questions at the end. Thank you.